we've seen the one definition of curvature, calculational definition, a common definition of curvature, and the notation. And we just re-emphasize that by saying that curvature is nothing but the magnitude of how quickly the unit tangent vector changes with respect to t divided by the rate of change of arc distance with respect to t. So that we're taking the t derivative of the unit tangent vector, but dividing by the speed with which we're moving along the curve, which is the rate of change of position on the curve with respect to t. And that is, again, the familiar expression that we used previously. We have an algebraic analogy, dt, d big T, d little t, over ds dt, which I mentioned previously. Just by algebraic analogy, dividing by this fraction is like multiplying by this fraction. The dt's divide out, and we end up with dt ds. And of course, this is an algebraic analogy. The calculus of why this works is not difficult, but we're not going to dirty our hands with that right now, or clean our hands, because that's kind of there's a purer way to see that, but we'll leave it at that for the moment. So curvature is the magnitude of the average rate of change of t with respect to s, and this again is the expression that we've had. Now we see one way to calculate a curvature. Another way, let's just consider this. Okay, here we have a curve with some parameterization r, and we might as well call that r of t, and r prime of t, r of t being our vector, and I'm not going to draw the r of t vector, but I am going to draw a vector representing r double prime of t, the acceleration vector. The unit tangent vector is just this r of t vector divided by its magnitude. If we project the r double prime of t onto a vector that's perpendicular to r of t, then we get, of course, the component of r double prime of t perpendicular to the direction of r prime of t. And this is going to be in the direction of our unit normal vector. We just have to divide this projection by the magnitude of the appropriate vector. And I've kind of lost my train of thought, so we'll come back to that, and we'll see what that vector is, because it's a little bit confusing. But what is the magnitude of this vector? Okay, if we divide this, back to my train of thought, if we divide this vector here by its magnitude, we're going to have a unit normal vector, and it might be more convenient just to calculate r prime and r double prime than to calculate r prime, divide by the magnitude of r prime to get the unit tangent vector, divide that by its or take the derivative of that and divide it by its magnitude to get the unit normal vector. So if we can get this vector, we can again divide it by its magnitude and so forth. Okay, so what is this vector? Well, this vector is related to this vector and this vector. It's just the projection of this vector in a direction perpendicular to this vector. And the magnitude of this projection vector here, magnitude of the projection onto, well, I don't have a vector to project onto. Okay. Getting a little sloppy here. Okay, we got a projection vector. The magnitude of that projection vector is nothing but the magnitude of r double prime times the sine of theta, where theta is the vector between r prime and r double prime. Now, that motivates us to think about, well, if you think about the sine of theta, where theta is an angle between two vectors, let's just think about the fact that if we take r prime and multiply, do the cross product of r prime with r double prime, the magnitude of that cross product is magnitude of r prime times the magnitude of r double prime times the sine of theta, so that this projection vector that we haven't yet named and haven't yet calculated, but the magnitude of this projection vector is nothing but the magnitude of r prime cross, almost made an asterisk out of that, r double prime divided by the magnitude of r prime. Okay, so we're going to use this fact in a minute to come up with a formula in terms of r prime and r double prime and its cross product for calculating the curvature.